chapter 16, we have studied that a rigid body can have three different types of motions. One is pure rotation. That's the one, as you can see in the figure. The wheel is a rigid body and it's undergoing pure rotation. That means the center of the wheel does not move from its position, but all other points they have rotational angular velocity. Second type of motion is translation, where all the points on the body they have the same velocity. And the third one is general plane motion, which is combination of rotation and translation. So let's start with this. So this is the example of pure rotation, where the wheel rotates clockwise. You can assume that the wheel lies in xy plane. Then the axis of rotation is perpendicular to the xy plane, that is along z-axis. Let's look at this question. So the question is, this center point, again, you can follow my cursor. So this center point, this is the center point of the wheel. Is it a permanent center point? That means if the wheel keeps on rolling in this position, will this center point change its position? And what is the velocity of the center point? You can pause the video for now and you can think about the answer before I give you the answers. Okay. So here is the answer, and the first answer is yes, this is the permanent center point. That means as long as the wheel keeps rotating in this position, this point does not change. It always remains as the center point of the rotation, and the velocity of this point is 0 because this point is not under rotation or translation motion. Then I ask you next question. What is the direction vector for this angular velocity? An angular velocity of the wheel is clockwise. You can apply right hand rule and determine the positive direction for this angular velocity. And the correct answer is, if you apply the right hand rule, that means if you take your right hand and bend your right hand fingers in the direction of omega, then the thumb, keep your thumb open, then it points towards the direction of positive value for the omega. So the direction of omega in this example is going down. If I assume that the positive z-axis is going up, then direction of omega is along negative z-axis. One more question. Consider the point A on the wheel as shown in the figure, and this yellow arrow indicates the position vector which connects the center of the rotation with the position vector with the point A. This point is actually on the wheel, so as wheel rotates, this point A also changes its position. But if you assume the snapshot condition, that means assume that you take the photograph of this wheel, and in the photo, point A remains stationary at this point. Then what is the velocity of point A? What is the magnitude of velocity and the direction of velocity at point A? So this is the position vector, this is omega, and now we can apply again the right hand rule and the cross product to find out the magnitude and direction of velocity at point A as shown in the figure. So you can pause the video, think about the answer and proceed further. And the answer is here. The magnitude and direction of velocity v in this situation can be obtained using the right hand rule. So velocity vector is always perpendicular to the position vector that is drawn from the center of rotation, and it points towards the direction of rotation. So this is position vector r, velocity v is perpendicular to r, so always this angle is 90 degree, and it points in the direction of rotation. The magnitude of this velocity is the product of angular velocity with the distance from the center. So it's omega r. Its both magnitude and direction can be calculated using cross product of omega with r. So it's omega cross ra, where ra is the position vector for point A. You can also apply right hand rule if you know the direction of omega, which is going downward here, and direction of r, which is as shown in the figure. You can find out direction of v using right hand rule. And to apply the right hand rule, you can focus on this figure here. So if you initially keep the fingers of your right hand open, so straight, put your fingers in the direction of omega, so omega is going down, and then twist your hands and bend your fingers from omega to r. So when you bend your fingers, as you can see, from omega to r, and twist your angle such that your palm remains perpendicular to vector r, then the thumb, which is open, gives the positive direction for the velocity. And that's the another use of right hand rule to determine the direction of the output vector for cross product. So this is revision. It's not new. We have seen it before. So how to calculate the velocity for pure rotation? Next question. So consider the case of translation. So in this example, a wheel slides without rotating. This word, read this one more time. Wheel slides without rotating. So wheel does not rotate. Wheel just stays as it is and it slides on this surface. What are the velocities of all points? The velocity for the center point of the wheel is, let's say, v. What are the velocities of all other points when the wheel slides without rotating? Okay, you can pause the video and think about the answer. And the correct answer is that all the points, they have the same velocity because wheel does not rotate. So wheel is under pure translation motion, and in translation all the points of the body, they have the same velocity, and there is no relative velocity between 2 points. So they all move at the same v. Okay, so this is the example of pure translation. Now consider the third example of general plane motion, where wheel rotates without slipping. So in this example, wheel rotates as it goes from left to right, and there is no slippage of the wheel. That means it does not skid, it simply rotates. And the same question, what are the velocities of all points? This is the example of general plane motion because wheel not only rotates, but it also translates from left to right. So it's combination of rotation and translation, and hence it's called general plane motion. And the angular velocity of wheel is omega, as shown in the figure. By the way, what is the direction of omega in this example? Think about the right hand rule. So if you bend the fingers of your right hand in the direction of omega, then the thumb goes inside the screen, and that is the positive direction for omega. So omega is perpendicular to the PowerPoint screen and it goes into the screen. So let's study this situation like general plane motion in more detail. So the point A is in contact with the ground at the given instant. Hence it has zero velocity because when two bodies are in contact, at the point of contact, they both have the same velocity. And because ground does not move, the velocity of the ground is zero. So point A on the wheel must have the zero velocity at the given instant. Be careful, we are saying that it's zero velocity. That does not mean zero acceleration. Acceleration can be non-zero even if the velocity is zero, because acceleration depends on the rate of change of velocity. So it does not depend just on one point velocity, but it depends the velocity before this point and after that point. And it may or may not be zero, hence acceleration is not necessarily zero when the velocity is zero. This yellow arrow is the position vector from the ground to the center of the wheel, and then the velocity is perpendicular to that point, and its magnitude is omega cross r, or omega r. So where omega is the angular velocity and r is the radius of the wheel and v is the velocity of the wheel. Now this paragraph here is very important paragraph. At the given instant, A has zero velocity. So we have already discussed that in the previous slide. Means A can be considered as the center point if we assume the pure rotation. So remember that in pure rotation motion, the center point has zero velocity. So we can say that A is a temporary center point for the wheel. However, it's not permanent center point, but it is the center point at the given instant. Let's say as the wheel rotates further, B point will come in contact with the ground and B will become a new temporary center, and then C, and then D, and then E. But at the given instant, A is the center point. Hence, A is called the instantaneous center, or IC. So now onwards, we will use this acronym IC, which stands for instantaneous center. Means the center point at the given instant. Right now, A is the zero velocity point and A is the center point. So if we assume that A is the center point, then we can consider this wheel as a big disk, as shown in the figure, whose center point is at A, and all these are the points on the disk, and the disk is under pure rotation. So remember how we have replaced the rolling wheel from general plane motion to this big wheel which is in pure rotation. And for that pure rotation, center point A at the given instant is the instantaneous center, or zero velocity center, and these are all the points on that disk. So at the given instant, entire wheel can be assumed to have pure rotation with respect to the instantaneous center A. Velocities of all the points can be calculated using the same rule as applied to pure rotation. So now I use blue arrow for the velocity vector and yellow arrow for the position vector. So velocity of point B, if I need to calculate it, then in pure rotation motion, we need to draw the position vector that goes from the center point to the point of interest, and the velocity is perpendicular to that point and always points in the direction of rotation as per the right hand rule. So the velocity of point B can be calculated by drawing this position vector and then applying the cross product of that position vector with omega. Okay. And this vector is the vector which goes from instantaneous center to the point of interest. So now, can you pause the video and draw the position vector and velocity vector for all the remaining points? That is points C, D, and E. And I'll give you the answer. And these are the answers. So velocity position vector for point C is this yellow line, which is from the center of rotation, instantaneous center, to point C. And this blue arrow is the velocity, which is perpendicular to position vector from instantaneous center. For point D, this yellow line is position vector, and this is velocity vector. For point E, this yellow line is position vector, and this blue line, which is perpendicular to position vector, is the velocity vector. So which point on the wheel has the highest velocity? That will have the highest value of this blue arrow. Think about it. So that's our next topic actually, which is topic 16.4, instantaneous center of zero velocity. And the objective is to locate the instantaneous center of zero velocity and use the instantaneous center of zero velocity to determine the velocity of any point on a rigid body in general plane motion. So the main application of instantaneous center is that it will let us convert the general plane motion of rigid body into pure rotation, and thereby it simplifies the calculation. And this is applicable only for velocity analysis, not for acceleration analysis. So you should be able to answer these two questions. If applicable, the method of instantaneous center can be used to determine the blank of any point on a rigid body. And the correct answer is A, velocity. Question 2. The velocity of any point on a rigid body is blank to the relative position vector extending from the IC to the point. So we have seen it before that the velocity is perpendicular, always perpendicular to the position vector drawn from the instantaneous center to the point. So the correct answer is B, always perpendicular. Application. The instantaneous center of zero velocity for this bicycle wheel is at the point in contact with ground. The velocity direction at any point on the rim is perpendicular to the line connecting to the point to IC. Which point on the wheel has the maximum velocity? And the answer is the topmost point, because all the points, for all these points, they have the same value of omega, and velocity is the product of omega and r. So the one which has the maximum r, maximum length of the position vector, is the point that has the maximum velocity, and that point is here on the top of the wheel, for which the r is all the way from the instantaneous center to top, which is nothing but the diameter of the wheel multiplied with the angular velocity, and that is the maximum velocity at the top point. So does a larger wheel mean the bike will go faster for the same rider effort in pedaling than a smaller wheel? We have discussed this before as well, and the answer is yes. For the same efforts, that is for the same angular velocity, excuse me, the bike with the larger wheel has higher velocity. So now for the next couple of slides, we will see how to determine the instantaneous center from the given diagram. Okay, so in this example, this is the board which is like supported at the wall and on the ground, and then we assume that the end A of the board slides left, so end B will slide down, and this board will have general plane motion because it will rotate and translate. And how do we determine the instantaneous center? We know one fact for the instantaneous center. If we know the direction of velocity vectors for both point A and B, we can draw lines perpendicular to the direction vector for A, which will be the position vector for A, and we can do the same for B and draw the perpendicular line, and where these two perpendicular lines intersect, that is our instantaneous center. So at the given instant, this is the center point, and the entire body AB can be considered as having the pure rotation rather than general plane motion with respect to IC. And then it's very easy to calculate the velocity for any point on the board as well as the angular velocity once we locate the instantaneous center. And this slide basically explains the same concept. Now for any body undergoing general plane motion, there always exists a point in the plane of motion at which the velocity is instantaneously zero, provided that it's a rigid body. This point is called the instantaneous center of zero velocity. It may or may not lie on the body. So you can see in this example, previous example, that instantaneous center is outside the body. The body is only AB, but instantaneous center is outside the body. So that's perfectly fine. If the location of this point can be determined, the velocity analysis can be simplified because the body appears to rotate about this point at that instant. Again, I keep on emphasizing the word at that instant because as the board starts sliding, let's say this point A moves further left and point B moves further down, same point IC is not constant, then we have to determine new instantaneous center by drawing two perpendicular lines from A and B and find the intersection point. Okay. So location of instantaneous center. How do we determine the location of the instantaneous center? So let's say we have 2 points A and B on the rigid body. This blue blob is the rigid body, which has the counterclockwise angular velocity. And then this is the velocity at point A and point B. To find the instantaneous center, you draw a line perpendicular to the velocity vector and extend it. From B, you draw another line perpendicular and extend it. And wherever it intersects, that is the instantaneous center. And velocity of that point is 0. So VIC is 0. And now this line, which is drawn from instantaneous center to point A, is called the relative velocity of A with respect to instantaneous center. See, we use here relative notation and not the absolute notation because this instantaneous center is not permanent. Okay, so that's why we have to use relative notation. So it's A with respect to IC and this is B with respect to IC. So this is one way when the two velocity vectors are given. Next question is, how do we find instantaneous center when two velocity vectors are parallel? For example, the velocity vector for A is going right and velocity vector for B is going left, but they both are parallel. So if we draw a perpendicular line from A and perpendicular line from B, they don't meet at one point. So instantaneous center can line anywhere on this line, but what is the exact location of IC? By the way, pay attention here that this arrow for VA is smaller compared to the arrow drawn for VB. That means point A has less velocity compared to point B. The length of the arrow indicates depends on the magnitude of the velocity. So now to exactly pinpoint the instantaneous center along line AB, the method is to join the tip of arrow A with the tip of arrow B. So you draw this one more line here, and wherever this line intersects with this line perpendicular to B and VB, that is the location of instantaneous center. Next here, so we have now two velocities. They both are parallel and point in the same direction, but they have different magnitudes. So point A has velocity which is right, and point B has also velocity which is right, but A has less velocity and B has higher velocity. And how do we find just from these two magnitude of velocities the location of instantaneous center? So for that, you draw a line which passes from A to B and extend it vertically up, and then you draw another line from A to B from tip to tip of velocity vector and extend it, and wherever it intersects with the first line drawn from the tail of both the arrows, that intersection point is the instantaneous center, and that's how you find the instantaneous center. And the last question is, if the rigid body is has two instant velocity vectors and they both are same magnitude and parallel, where is the location of instantaneous center? So for example, if I say that the arrow A has the same length as that of arrow B, then this line will never intersect with the line drawn from tail to tail, because this line will go up and this line will also go straight up in parallel. It's like the railway tracks, but they will never intersect. So where is the location of instantaneous center in that case? Think about it. And what does it mean that both the velocities have the same arrow, like 2 points? And the correct answer is, in that case, the intersection will happen at infinity. And if that is the case, then the length of the position vector from the instantaneous center to point A and point B will also be infinity. So if you calculate the velocity, if you write the equation of velocity, V is equal to omega multiplied by R, R is infinity. So the value of omega will be 0, because omega is V divided by R. So it's V divided by infinity. Anything divided by infinity is 0. And that means omega is 0, and omega is 0. That means rigid body does not have any angular rotation. It's pure translation. And that also justifies the length of two velocity vectors same, because if it is in pure translation, both the points have the same velocity. So yeah, we have pretty much discussed everything as far as the theory is concerned. Now the next thing I will do is I'll do the in-class exercise. I'll solve the problem. However, that problem is not just for instantaneous center, but it's actually for acceleration analysis, which is the next topic for the next lecture. But for any acceleration analysis, we have to first do the velocity analysis.